Hey everyone, welcome to this explainer. I'm so glad you're here, because today we are unpacking what is honestly one of the most fascinating mathematical mysteries in modern machine learning. We all know that training artificial intelligence is notoriously complex, it's chaotic, and yeah, it's incredibly expensive. But what if I told you that some really clever researchers recently discovered a massive, hidden shortcut right in the middle of all that chaos? Today we're looking at a breakthrough called RELEX and how it literally fast-forwards AI training. Let's get right into it.
I want you to hold this one central question in your mind as we go through this. What if we could predict the future of an AI model's training without actually computing all the complex math required to get there? Usually, training a large language model, well, it feels a bit like navigating this dense, unpredictable jungle. But researchers asked a super provocative question. Does this chaotic optimization process actually have a hidden, perfectly predictable secret?
And the answer, amazingly, is yes. And this number right here, this is the proof, 15%. Researchers have discovered that by looking at just the first 15% of an AI's training process, they can accurately extrapolate the rest and achieve the exact same performance as a fully trained model. I mean, think about that for a second. Skipping 85% of the computational heavy lifting, that translates to massive, massive savings in time, energy, and obviously money.
Okay, let's dive into Section 1, the AI training bottleneck. To really appreciate this solution, we first have to understand the huge roadblock that this research is actually solving, the sheer crushing cost of training these large language models. You see, to get AI to actually reason, to solve complex math or logic puzzles, researchers use a technique called reinforcement learning with verifiable rewards, or RLVR for short. And RLVR is absolutely incredible. It's the engine unlocking advanced reasoning capabilities in modern models. But it has a fatal flaw. It requires running models through massive optimization steps, scoring responses and updating parameters token by token. We're talking days of incredibly expensive GPU time. This massive bottleneck sets the stakes for our entire scientific detective story today.
So, how do we get around it? This brings us to Section 2, the hidden linear pattern. We have to look for patterns in the noise. For this next part, I want you to put on your detective hats as we investigate a very chaotic, high-dimensional space. To solve the mystery, researchers shifted their focus away from the overwhelming macro scale of AI training, and instead, they asked a very physical question. Where exactly are the model's parameters, its weights, actually going? Like if you track a model's weights from the start of reinforcement learning to the very end, what does that path physically look like?
And this brilliant visualization illustrates the massive aha moment of the paper. Over in the raw weight space, the training trajectory is curved, it's messy, it's basically impossible to predict. But the researchers applied a mathematical transformation called singular value decomposition, or SVD. When you project that same messy training path into the SVD space, that curved trajectory magically transforms into a perfectly predictable straight line. It's almost unbelievable.
If you aren't super familiar with it, SVD is essentially a mathematical decoder ring. A model's weights live in a massively complex, multidimensional space. What a Rank 1 SVD does is filter out all that noise and isolate the single dominant direction of change. It turns out that during RLVR training, almost all the meaningful learning is happening along just one primary mathematical vector.
Let's see how this builds across actual model parameters. If you look at the Rank 1 SVD coefficients plotted over training steps for the Qwen AI model, just notice those pink lines. That coefficient evolves almost perfectly linearly. We are talking about an R-squared of over 0.98. In statistical terms, that means this path isn't just a loose trend, it is undeniably incredibly predictable.
Which leads us to Section 3, fast-forwarding with RELEX. Because once you realize the path is a straight line, the solution actually becomes kind of obvious. Let's look at how researchers turn this mathematical observation into a literal cheat code. RELEX, which stands for Reinforcement Learning Extrapolation, bypasses expensive GPU training using 3 completely training-free steps. Step 1. Observe the early training data and estimate the dominant trajectory using SVD. Step 2. Fit a simple straight line to those early data points. And Step 3. Use that line to predict exactly what the weights will be hundreds of steps into the future. That's the whole shebang. No complex gradient descent, no heavy compute, just a simple linear regression. Now, if the math is sounding a bit abstract, think about it this way. Imagine you're watching a runner on a track.
If you watch them for just the first 15% of their race and you notice they're running at a perfectly constant speed, in a perfectly straight line, well, you don't need to stay and watch the rest of the race to know where they'll end up. You know exactly where they are going to finish. RELEX simply calculates where the AI is running and skips straight to the finish line.
And when we look at the actual benchmark data, the results are stunning. Notice the compute cost here. RELEX uses just 15% of the resources of full RLVR. But look at the performance scores. On the standard math benchmark, RELEX exactly matches the fully trained model. But on out-of-domain benchmarks, like AME25 and HMM25, RELEX doesn't just match the expensive model, it actually beats it. It's getting higher scores while using a fraction of the compute.
To really visualize this precision, we can map out test accuracy over training checkpoints for 3 different Qwen models. The black and blue lines, those show the slow, expensive, fully computed training path. But notice the pink dots. That's RELEX. Based purely on that early 15% of data, those extrapolated pink dots perfectly hit and sometimes even surpass the final performance target of the fully trained models. It is beautifully precise.
But this brings us to a final, very compelling mystery in Section 4, Denoising the Future.
I mean, we can all understand how a mathematical shortcut saves time, sure, but why on earth does it actually improve performance on completely out-of-domain reasoning tasks? Well, the answer lies in what the shortcut leaves behind. When we do that SVD projection, we find that the primary rank 1 direction, component 1, explains a massive 81.4% of the parameter updates. The other 18.6% is spread across higher rank components. So what exactly is in that 18.6%?
Take a look. Component 1 is a smooth, beautiful, linear signal. But if you look at components 2 through 5, they are wavy, they're chaotic, they're incredibly erratic. This is optimization noise. By only fast-forwarding the smooth component 1, RELEX acts like a filter. It essentially tunes out all the erratic radio static of the training process, so the AI can actually hear the music clearly. So the absolutely crucial point is this: the RELEX shortcut is technically a spectral denoiser. Standard reinforcement learning kind of wanders around a bit, picking up bad habits or overfitting to specific training data. That's the noise. By forcing the model to just extrapolate the straight line of the primary signal, RELEX skips all that erratic optimization drift. And that is exactly why it generalizes so much better to new, unseen problems.
The paper summarizes this entire phenomenon with a really brilliant observation. RL training carves surprisingly simple paths in low-rank parameter space. Think about that. For all the billions of parameters and the millions of dollars spent on GPUs, these incredibly complex models ultimately just want to follow beautifully simple, straight geometric lines. We just had to know how to look for them.
And that leaves us with a massive question to ponder as we wrap up. If the emergence of advanced AI reasoning is governed by trajectories that are this predictable and this linear, what other impossibly expensive training bottlenecks in machine learning are really just straight lines, just waiting to be fast-forwarded? Thank you so much for joining me to explore the RELEX paper today. I really hope this completely changes how you look at the future of AI training.